So, in detail, what can we see? Surface features. Right, I have emphasised these. I'd like to say this was done by automated processing, but it wasn't. This was manual tracing of the features. In blue, meltwater channels, surface linear features caused by, I'll show you what one actually looks like in the flesh in a minute, caused when surface meltwater runs down the surface of the glacier. We can see lots of these, active ones and relative ones. In green, in almost invisible green here, a system of crevasses. You can see there's a tributary glacier here, which actually makes a really sharp turn as it comes down to there. So the ice is creaking away like anything, and it's very crevassed. And there are some crevasses there as well. I think. No? Okay. So if we zoom in, you can see that a bit more clearly. So this is the same slope-shaded digital elevation model there, and you can see these meltwater channels very clearly. This is what one of those meltwater channels actually looks like. If you stand next to it, there's Neil Arnold with scale. And this meander here is that meander there. So you can see that. So that's an active one. Here is the system of crevasses. That's just a blow-up of what you can see before as well. Here are the crevasses as that is the glacier turns the corner. I think there's something else tucked in here as well. Yes, okay. Comparing two dates. So we have an acquisition in 2003, an acquisition in 2005. Well, the obvious and very much desired thing to do there is just to compare the surface topographies. How much did the surface of the glacier change between those two dates? Well, most of it went down, which wasn't a big surprise. That's what this glacier is doing. Here is the glacier from the snout up to the here, here, and this is color-coded, and then I put the numbers on as well to show the average mass balance water equivalent. So this is meters per year water equivalent in different parts of the glaciers. The different colors represent different values of the mass balance. The average over the whole glacier is about minus 67 centimeters per year. Corrected for the fact that this isn't quite 2 years of data. And that was quite interesting because the in situ measurements, the measurements that were acquired by measuring the stakes that had been bashed into the surface for this same period, gave a much smaller, in a sense, as not as negative value for the mass balance. And that's not the first time this has been seen. There have been other studies using digital elevation models, differenced over time, which have found more negative mass balance than you get from measurements of stakes. You're probably going to ask me why that happens, and I'm going to tell you that we don't yet know. But it is clearly a matter of concern. Marginal retreat. So here are, what we're actually looking at here is the 2005 LiDAR acquisition, again slope shaded. And what I've done here is I've traced, again manually, I'm ashamed to say, in green, the snout configuration in 2005, but in red, I've done the same thing for the co-located 2003 acquisition. So red is where the snout was in 2003, green is where it was in 2005. Here is a graph showing a transect. The transect runs like that, showing the altitude along the transect, showing where the transect was in 2003, that's the upper set of dots, and where the transect was in 2005, that's the lower set of dots. You see, reassuringly, the dots absolutely line up on top of each other below there, but in this region here, they're separated. So what's happened is the margin has retreated from there, 2003, to there, 2005. And that translates, that was about 13 meters of retreat, so that's 13 meters into the year, so about 6.5 meters a year. And you can also see a drop in height as well. It's not a big surprise. I mean, it's not a radically new observation that a glacier is in retreat, but it's a very detailed quantification of it. Now, it's quite interesting to put those changes in a longer context, and this is something that Helen and I were developing during an odd free moment in doing fieldwork in Svalbard. Here again is the slope shaded 2005 LiDAR acquisition, and here, I hope you can read the numbers, in yellow are the positions of the glacier snout, just done by digitising old maps, georeferencing and then digitising old maps. So going back from 1965, 77, 95, and then 2005, that's the one from LiDAR, and then 2010, we got that one this year, actually just by a very simple method of just walking along the snout, the margin of the glacier with a GPS, and then just grabbing the track along later. It was a bit of a messy operation because we kept falling in the mud, but it gave a position. So you can see that the change that we saw between 2003 and 2005 is quite consistent with the longer term changes that are happening. And here, in fact, this is a transect running approximately like this along the glacier. This is showing the elevation as a function of transect distance. That's how it was in 65. That dashed green line is how it is now. So the changes that we saw over that short period, which we got from the LiDAR data, are quite consistent with the long-term changes. More information from the LiDAR data. Now this is a particularly exciting one because it's such high spatial resolution and because it's capable of resolving the surface geometry sufficiently to show the meltwater channels. So here's a set of meltwater channels. You can see there's a little confluence there, in fact. We noticed that many of these features were equally visible in the 2005 and the 2003 LiDAR data. So we wondered whether they are sufficiently stable over time that they can actually be used as features that can be tracked to measure the